So it will be computational post-translational modification in proteomics, and it's also application in Maxcon. So my name is Şule, and I am a Marie Curie Individual Fellow at Jürgen Koch's lab here in Max Planck Institute of Biochemistry in Munich, in Germany. So, very hungry caterpillar. We know this, it's very classical kids book. And then in this story, we have very little caterpillar who's very hungry and eating all the time. And in the end, he turned to the butterfly. This is actually a classic example about the genome and profile, the genome and proteome. And what happens on this proteome level, a lot of signaling, a lot of changes. And most of these changes also happening due to the PTMs, because PTMs, post-translational modifications, are playing role on the signaling pathways. My today's talk, I will talk in the beginning, what are these post-translational modifications? And I will give an example, simplified example about the spectra for this modified peptide. I will briefly go through about peptide fragmentation and then fragmentation method. And I will show some part of the Maxcon, how you can set for your PTM analysis. Then I will explain a bit more detail how what Maxcon does for the PTM studies in terms of scoring, Undermodel scoring, and the localization probability and occupancy. And later I will show the remaining part, how to set Maxcon for your PTMs. So let's start about the post-translational modification. Post-translational modification, this covalently link some chemical groups to the protein. And then this change to the protein, it can give a new functions. So yesterday, during Skigi's talk, he mentioned several times of kinase. So what are these kinase? So let's talk about a very simple example here. Since during registration, we noticed that there's half of the people actually beginning, so it will be good time to set the base for everyone here now. So we have a protein, and then we have an enzyme called kinase. And this kinase transferred phosphate group from ATP to the protein. And now this phosphorylated protein has new function, and then it can convey some more function in our bodies. But there's also another enzyme called phosphatase. And here, what does this enzyme? Remove this phosphate group, and then the phosphorylated protein became only protein. This is constantly happening, and then it's basically mainly occurring on the serine, threonine, and tyrosine, which in the letter abbreviation we know S, T, and Y. This was very revolutionary to know this PTMs and this phosphorylation, and therefore the researchers who found them, they also got the Nobel Prize. So phosphorylation is regulating several processes, and here is some of the examples. So if you remember the little caterpillar, the cells is getting bigger, so there's a lot of cell growth occurring. And in the end, it's also become a butterfly, so there's also differentiation. So there's many processes are regulated phosphorylation, but not only phosphorylation is playing key processes in biology, but there are also some other modifications. So especially about this phosphorylation, the kinases are very drug targets, because when this kinase is not functioning very well, there might be some upregulation or downregulation of the phosphorylated proteins. And as a result, there will be some diseases, like the cancer is common study for phosphorylation cases in terms of drug development, or some other diseases. And there's a website called phosphosideplus, and then here we have enormous information about phosphorylation. So we know what functions they give, where they've been found, what about the specification and so on. The name might be misleading, but actually it's not only for phosphorylation. So there is some data set, it's also covering some other modifications such as ubiquitination, simulation, acetylation. And this data set will be also important tomorrow's Perseus tutorial about the computational PTM. So now we know the basics about the PTMs, and let's go and have a look how the spectra will look for the modified peptides. So here we have two peptides. Peptide A is unmodified and peptide B is modified. And as you see, modification is on the fourth residue, which is shown as a star. Imagine that this residue, its modifications actually give us the addition of mass, and on the MS level, we know that we will see a shift. And if you remember about this MS and MSMS, please, you could also refer to Pilley's peptide story. You know that we have some MS, but MS sometimes not enough, so we do the MSMS. And then let's do the MSMS on the unmodified peptides. And then we have some fragment ions. And in these fragment ions, we might have only one residue, or we might have more than one residues. And let's have a look at this modified peptide. We know that modification happens here on the fourth residue. And here, what we see, the common fragment ion, which don't have the residue, modified residue, is the same. It gives us the same M/Z. But any fragment ion that contains this modification has a shift occurred due to the mass of this modification. So let's briefly talk about the peptide fragmentation, because it also plays an important role in the computational wise, how we identify the peptides. So we know that peptides occur along the peptide bond. And in that case, in this example, we have actually 7 residues. On the Monday, there were several talks. They explain in detail. But here, what we know, the peptide cleavage can happen on the peptide bond, and then we will have B and Y ion. But can also happen on the amine bond, and then we will have C ion containing N terminus, and then Z ion containing the fragment of the C terminus. And it could be also possible fragmentation occurring one peptide bond before the peptide bond, and then in that case we have A and X. But in terms of especially modification, we have also additional information such as diagnostic peak and neutral losses. Sometimes the fragmentation can happen two-side, and then we have internal ion, such as ammonium. And here we have ammonium ion example. What we see is R. R is the residue, amino acid residue. And then this R can be phosphorylated tyrosine. And when this phosphorylated tyrosine ammonium is such a unique to show this phosphorylation, and then we observe this diagnostic peak in this case. And there are also some neutral losses occurring regarding to the phosphorylation, regarding to the modification as well. And there are some commonly used fragmentation methods, such as collision dissociation B and Y ion, or higher energy collision dissociation B and Y ion plus A2. And we have another one called electron transfer dissociation C and Z ion. Now let's have a look very briefly about this fragmentation methods. You know that CID gives us B and Y ion is informative, but it's not optimal to study modified peptide. On this example, we see the CID fragmented spectrum from this peptide. This peptide has 12 residues, and it has 2 phosphorylated serine sites. And what this spectrum actually gives us, mainly B and Y ion, but CID doesn't give us the low M/Z fragments. This is also known 1/3 rule. If our peptide also contains tyrosine, then we will have a diagnostic peak, but CID, we don't have such diagnostic peak, so we are losing such information, for instance. And more important, the labile bond, which modifications are attached, are actually cut out. And because all this many different fragmentation and also neutral losses and so, we have a noisier spectra. Noisier spectra compared to the SCD. This spectrum is the same peptides, And again, the fragmentation is before on the third and on the fifth residue. And we could clearly see the differences between these two. So what we see, we could see the low, we can observe the low M over Z values. So here, as you see, we were going up to 200, the minimum was 200, and here we could actually observing much lower M over Z values. If we have tyrosine here, we will also have the diagnostic peak there. And the second is we have less relatively unstable B ion, and then we contain mainly Y ions. And you could also see if we have mainly Y ions, and we still have some B ions. And this ion is actually more precise as well. And because this B2 ion is very stable, and then there's another ion comes from this is A2. And with this A2, we don't actually see it on CID fragmentation. And if we look at between these two spectrum, we could see the CID is more cleaner. We don't have this very noisy baseline here, like in CID compared to the SCD. There's another fragmentation method known electron transfer dissociation. But this is fundamentally different because here electrons are transferred from radical anions to protonated molecules. And as a result, we don't have the fragmentation on the peptide bond, but amine bond. And therefore, we have C and Z ions. And in this fragmentation method, the PTMs and side chains are left intact. So it's good to study PTMs, but we need to have higher precursor charges because we are losing some of the protons later during this electron transfer. And compared to the CID, it's also very slow. It's slow. And there's a lot of development going on. So they are combining ETD with some other fragmentation method to improve this further. Today, we will have a speaker, Coşkun, and Coşkun is the pioneer in this field with this electron transfer dissociation. Because of his contribution, he also got the Beeman Award from ASMS a while ago. So I'm looking forward to hear his talk also. Now let's talk about how to set up Maxcon for the PTMs. So here on the group parameter, we have a modification tab. And then we have two modifications defined here, variable modification and fixed modification. This variable modification, where we put the phosphorylation STY, serine, triosine, and tyrosine. And the other modification, as you may have seen, is fixed modification. It's fixed because we know that it's always there on this certain residue. And the other important settings here is not so much, but the maximum number of modification per peptide is default is set 5. Imagine that you have set it to 10, and then you were wondering why my search takes so long, because you're introducing a lot of possible options on database search, and your search is really taking much more longer time. So you are increasing your search time with this. So it's good, as yesterday Hamid was saying, keep the default as default unless you are really sure that something needs to be changed. And the second, so there's you could find the details about the PTMs on the configuration tab. So I told this phosphorylation, we target 3 different residues, and they give the neutral loss or diagnostic peaks. And then we know that there are neutral losses on the serine and triosine. And you could see which was the composition, which was the mass that Maxcon is considering. And the diagnostic peaks is in tyrosine, and then you could see the composition as well on this case. And if you want to know a bit further how you can set this configuration panel, please refer to one of the precursors given by the Christoph, was released a couple of days ago. Okay, now let's talk about Maxcon for PTM studies. So many things actually said in the beginning was done for the phosphorylation STY, and in 2014, when the Maxcon algorithm published in detail, the data set was also the phosphorylated phosphorylation-based dataset. So on this publication, in the computational pipeline, as we see, Maxcon has 4 main steps. So the data acquisition, where we know we get the raw file and we process them and we prepare it, and then we do the database search. And on the second step, we do the identification, and then there are some specific case for the modification. So we do some filtering based on modification for the modified peptides. And to reflect the certainty about localization, we had also localization probability is being calculated. And then we also had the occupancy calculated on this pipeline. So this data set will be also used for tomorrow's computational PTM tutorial on the Perseus. And then that's why I will briefly introduce what was the biological conditions as well. So there were 4 groups, and one of them is control, which they didn't do any stimulation. And the other one is mitosis. On this mitosis, we know that there's a lot of phosphorylation events occurring, and then we expect to see a lot of changes in that. And then in EGF, growth factor, which was done either 5 or 15 minutes. And the cool thing is about this, there was a lot of literature known, so it was easy. It was nicer to go back and check it. And the last one, the pervidinate treatment, and then we were doing it, and then we were stopping the signal and then see what was happening. So this part of this data set is the label-free quantification, and the depth was quite okay. The depth was 11,000 for protein and 50,000 for the phosphorylated peptides. Now let's go through about the second step on the Undermodel scoring. You have seen this the last days. For the Undermodel scoring, we have the one line about the experimental spectrum, and we have the second branch about the theoretical spectrum. So the theoretical spectrum is still prepared similar way. We still have BNY ion, and then BNY ion doubly charged if the precursor charge was bigger, and considering this is HCD or CID. And then we have some neutral losses. But for the modification, in addition to this peak, we have some peaks which has specific losses for phosphorylated serine and phosphorylated tyrosine. So if we have the phosphorylated phosphorylated triosine. So if it was phosphorylated tyrosine, we will have the diagnostic peaks. Based on your modified peptides, and in this case, we changed the algorithm based on the phosphorylation event, we changed the theoretical spectrum generation. And here you see that there's a little asterisk saying us score is calculated once with and once without loss of these peaks are added. Because we are not for sure if these losses are there, so we assume and we calculated Undermodel scoring when the theoretical spectrum contains these neutral losses, and then we calculated the same Undermodel scoring without this neutral losses added. And from these two, we take the maximum, and then we report this on this PSM, on the peptide spectrum mesh level. I told you that we have some filtering for this modified peptides, and then you can find this information on the global parameter under the identification. And here we have minimum score for the modified peptides is being set to 40. Why is it 40? Because back that time there was this synthetic peptide and phosphopeptide library, and based on this data set, it has been optimized for 40. And there's another filtering, which is minimum delta score for the modified peptide is 6. What is this delta score? Delta score is the differences between best score and the second best score with different sequences. So imagine that if you have two scores are very close for the same spectrum, it's not very likely the scoring function is not very good to identify. So if you have a bigger delta score, you will have a very strong confident about Undermodel score over there. Now let's talk about the localization probability. This shows us the certainty about localization. In this scenario, we have a peptide sequence, and then there are 3 possible linkable phosphorylation sites. One is serine, the other one tyrosine, and the other one is tyrosine. And because of the peptide mass, we know that there are 2 sites has been linked. So in Undermodel score, we calculate the Undermodel scoring engine. We calculate the score, the first peptides, and then we calculate the score for the second peptides and the third peptide. As you see, there will be shift on the spectrum because the PTMs are different located on this peptides. And then we have the 3 different Undermodel score, and we take the exponential of it, and then we have the probability for each case. And in the end, we use the normalized combination of all possibility about this modification. So I told you this tell us the certainty of the localization, and there are some studies going on, so it's already has been conducted. And then for the class 1, shows the identification based on this localization probability. And instead, if you have at least 0.7 to 5%, you have a well localized identification. You have a higher confidence on your data set. Now let's talk about occupancy and how we can use it. So occupancy is the fraction of the protein for which the site is modified. So in this scenario, we have 2 conditions, condition A and condition B. And we could see that the PTM is being changes too, but is it really reflecting the changes on the proteins which will be inside modified? So the better way to actually report this will be the calculating occupancy. In order to show the occupancy, how it's being calculated and introduced on the paper, so we will go one by one, and then we will fill this table. So on the table, for each condition, we have number of phosphorylated peptide, number of unmodified peptide, and number of total peptide. So we will get the first number of phosphorylated peptide, and this dot, the purple dot, shows that this was phosphorylated, and darker shows the peptide. So here we have 1, and then here on the condition B we have 2. And here, unmodified peptide-wise, on the condition A we have 2, and then B became 1. The total number of protein, however, they stay the same. So the question is, can we really directly compare the phosphorylated peptide against unphosphorylated peptide? Already I put the answer there, but we cannot compare them because the phosphorylated peptide are different, for instance, flyability on the mass spectrometry instrument. So because the phosphate group, it changes the physical property. So instead of comparing against each other, we can compare their ratios. So we will need the modified peptide ratio, we will need unmodified peptide ratio, and also the protein ratio. After we can know them, we can calculate, as given on this Curtis paper during Maxcon detail, we can calculate the proportion known as A. This was the number of phosphorylated, number of unphosphorylated, the ratio about the phosphorylated and unphosphorylated. And when we put this A, we can get the occupancy information. And why is it good for? So it can be informative to measure the state of the system. So it can tell us what's happening. But as you will see on the tomorrow's Perseus tutorial, we perform the statistical in terms of ANOVA and so on the intensities column, not on the occupancy column, not on the occupancy. So here on this paper, on the Curtis paper, the occupancy of phosphorylated peptides are shown on the x-axis, and then we have the frequency of this occupancy. And in the control group, we didn't do any stimulation, so it was as as no. And then on the mitosis, we know that there's a lot of phosphorylation events is occurring, and then we could also the changes compared to the control group. And then EGF is more very similar to the control group because it's like this. It doesn't so much changes occur on that stage. When we look at the tyrosine occupancy, we see a different scenario because we know that tyrosine is not so much on the mitosis, but peronedates. We already expected this. So if you want to know for more this explanation, please go to the paper and then you will get more also information about the data set itself. And how we can set up the Maxcon for the PTMs. So occupancy will tell us the fraction of protein about modification, and occupancy will be good to know, but we need to have the complete proteome in addition to phosphoproteome in our experiment. And you need to introduce them together in the Maxcon. And here, the green part shows the phosphorylated, the data set was normal proteome. We don't do any enrichment on the phosphorylation. And then here, we have the data set has been enriched for phosphorylation. And then we know that there are two different groups, and groups will be crucial because we will put the second group, the phosphoserine, threonine, and tyrosine, but we will not put it there because we don't expect to see the changes on the tyrosine, so phosphorylation level here. And they are all different experiments, and then we don't have the fractionation. And here we have the PTM column, and then we tell to Maxcon which one the PTM study, and then it needs to know in order to calculate the occupancy. If you don't do any phosphorylated sample or so, if you don't have these two different data sets, you don't need to put this, you don't need to change the PTM sign. If you want to know more how to run the Maxcon analysis, you could refer to Daniela's pre-course that she showed nicely how you can run the Maxcon. Sometimes people are like, okay, I did it, but I don't have the occupancy reported on my table. Or there's no occupancy. Why? It could be because you don't have enough depth on your proteome, so you need to go deeper. And in this case, we show an example that for the replicate one, we have this 5 different raw files. And then for the replicate 2, we have again 5 different more. So it's also good hints. And when you also do the label free for your phosphorylated studies, you need to have the reference sample is different. You shouldn't choose the similar one, then you will have the error propagation related issue on your occupancy calculation, which we avoided with estimation, but still you need to, on the LFQ, find the reference much different than the others. So what does it mean two-fold change? You need to also be very careful when you say about the fold change. So is it really the fold change related to the number of modified peptides, or is it about the proteins? So in this case, we could see that the modified peptides double, but it's really double. No, it's not, because the protein ratio has been double. So you need to also be careful about this fold change. So in the conclusion, even though, you can use Maxcon for your PTM analysis. And in this example and the previous, we focused so much on the phosphoserine and tyrosine, but you can entirely reduce any other modification, and then you could find some other modification on already predefined one on the modification column. In case you don't know which modification can be on your sample, you can perform dependent peptide search. And this dependent peptide search will be covered today, Jürgen's talk on the Maxcon Basics 4. We talk about a lot of fragmentation methods, and then do you really need to care about this? This is really the beauty of Maxcon. As a user, it's also very friendly because you don't need to worry about this vendor-specific details. So Maxcon will go and parse the raw files, and then we'll find which fragmentation method is being used and then use it for the undermodel scoring. But this knowledge is still good to know in terms of PTM. And then during undermodel scoring, some modification-specific information was added. As you remember, we had on the theoretical spectrum level, the theoretical spectrum are different, and we had some PTM-specific information. And then the second, on the global parameter, we have also the filtering. So if this was defined for phosphorylation, but you can try with this default setting, and then if you are having some other PTMs, you could make some plot, and then you can say, okay, maybe I should increase, and maybe I can change it, and then you can see the effects on your example. And localization probability will tell you, reflects the certainty about this the site. And if you want to do more automated ways, there are different classes, and 0.75 class will it should be at least 0.75, and it will give you better identification. And then you need to have a full proteome for your occupancy calculation, and you need to be careful what fault chain actually tells you. And with this, I want to thank you. And please also sometimes remember what was happening on this little caterpillar during butterfly processes. It's also some PTMs going on. And with this, I want to emphasize that I will read the first tutorial tomorrow about computational PTMs, where we have the output table from this original publication of the Kirti, and then I will show you how you could use the per series to get most out of it. Thank you.